Hi, my name is Mateusz Kozłowski and I'm a cloud software engineer working at Intel Corporation. I'd like to present to you the software storage solution named Cloud Storage Acceleration Layer, CSAL for short, that has been released as part of SPDK version 22.09. As the name suggests, CSAL has been designed primarily for increasing the performance of workloads targeting big data, requiring large worksets, which in turn require high-capacity SSD drives for backing storage, though we'll get to the details for those in the further slides. During the presentation, I'd like to first talk about the problems the CSAL is designed to solve, the overall architecture, both current as well as past we expect the software to expand to. Then we'll take a look at the performance results, micro benchmarks, as well as the larger storage benchmark suits. We're also going to see a quick guide on how to create and use the necessary components as well as their requirements. We'll finish it off with the direction we expect the software to evolve into, short term within the upcoming SPDK release, as well as the long term. We'll start with the overall problem that CSAL is designed to solve and what trends are happening in the big data world. The primary driver for the solution was the partnership between Intel and Alibaba. So the perspective given here is from the cloud service provider and their immediate client's point of view. As new generation of CPUs were appearing with higher number of CPU cores available, the bottlenecks were beginning to be seen in the storage layer. It turns out that during the Hadoop and Spark workloads, there exists a required ratio between the number of virtual CPU cores and the size of the storage, which in Ali's case was around 1 CPU core requiring 2 TB worth of HDDs. So with the number of cores increasing, the solution before was straightforward: increase the number of disks. This worked until you start to run out of space in your server. With HDDs, you can't really scale the density by upgrading to, say, 4 TB drives. The capacity doubles, but the performance stays the same. It doesn't scale up, and a bottleneck at the storage layer is introduced. So for a given performance level, you'd level out at around 48 TB worth of capacity in a server until you start bottlenecking. So the goal here was how to increase the amount of data that can be analyzed. And the obvious first solution is to use QLC drives. They're cheap, provide plenty of capacity, and overall would consolidate the number of racks required by increasing the amount of data stored in each server. However, it turns out that the performance wasn't quite there, and this approach was also leading into endurance issues. So let's now talk about the problems that QLC drives themselves are having, both in the specific case and in general. The first one is the performance scaling. While not quite as bad as HDDs, here the performance still declines with density. The capacity rises, but the ability to access it still increases over time when jumping between SLC to MLC, TLC, and QLC. Second is the endurance. Higher densities require much more precise voltage levels to be written and read from. This means that data needs to be rewritten more often by the firmware in order to prevent data corruption, as it needs to be triggered earlier to comply with these tighter voltage requirements. The drive writes per day decreases with each generation and is hit especially hard in random workloads, as the internal garbage collection amplifies these problems. Third is small random writes. In order to drive the costs down, especially the QLC drives will often store data using larger indirection units. Instead of 4 kilobytes, same as the sector size from the user point of view, it may store it in 64 kilobyte units. This means that the mapping table used in drives can be smaller, reducing the price. It comes at a cost though. If the incoming write is not aligned with these units, it incurs a penalty. A read modify write operation is needed. This causes two issues. Not only is the performance decreased, but the already lower endurance takes a hit as well, as more writes are generated. Finally, multi-tenancy. If multiple users are writing to the same drive by, say, splitting it into partitions and utilizing in their own VMs, their data is still mixed together inside the SSD. This means that even if one tenant is writing nice sequential 64 kilobyte data, its performance may drop because someone else is executing random 4K workloads at the same time. So to sum up, we require from the solution to bridge the scalability and performance gaps, while still bringing the total cost of ownership down. Let's take a look then at the high-level architecture. The main component of CSAL is the FTL, or Flash Translation Layer, which is both a BDEF module and library in SPDK. It is very similar architecture-wise to what firmware is executing inside of a NAND SSD, though with a few differences. First, all logic is executed at the server level, which allows to create many scalable virtual disks in a storage box, whose characteristics are easier to fine-tune to the needs of the user. The logic inside FTL is lockless, which allows it to make these scalability goals more achievable. CSAL makes use of a persistent write buffer as a write-back cache for user data, but it's also used to store most of FTL's metadata. The drive in this slide mentions Intel Optane SSD as the cache drive, but assuming a few key requirements are met, which I'll get into later, SLC drives can also be used. On the bottom, we can see the pool of high-density NAND, against which most of FTL logic is run against. This is where most of the magic comes into play, shaping writes in such a way to avoid the problems of cheap NAND. Finally, we have the L2P, or logical to physical table. Similarly to what's happening in NAND SSDs, we need to map the LBA from the user point of view to the physical location on the drive, and in CSAL's case, also needing to address which drive to point read requests to, cache or the NAND pool. Usually, L2P takes a fairly significant chunk of memory, roughly 0.1% of the size of the surface drive, which for a 16 TB QLC would be 16 GB. However, in order to decrease these DRAM requirements, CSAL implements a least recently used cache for L2P, storing only the hottest portion in DRAM, paging other parts in and out as necessary with the persistent write buffer. So to sum up, CSAL's high-level goal is to capture writes in the persistent write cache, aggregating them into larger write sizes before submitting them to the NAND. All of this needs to be power fail-safe, meaning any crash at any point in time of either the OS or SPDK application needs to be both recoverable, and any writes reported as completed to the user must be restored faithfully as well. Now we're going to fill in this slide with some extra information at each of these steps. First off is the interface to the Flash Translation Layer. The goal here is to allow the user of the module 4K random block access to the high-capacity NAND media, meaning it will behave exactly as a standard black box block device. This is in contrast to a potential other answer to the QLC problem, zoned namespace drives, which require sequential access only and require specific management steps inside the I/O logic. CSAL is able to boost the performance of QLC by submitting user writes to the persistent cache and aggregating very large amounts of them, currently about 1 MB, before submitting the data to the NAND. This allows for reduced write amplification factor in their NAND, as the number of read modify writes has been virtually eliminated. FTL has also implemented internal garbage collection mechanisms in order to allow for this continuous large block size writes to operate. It's able to recover from power failure, OS and SPDK application crash, regardless of any I/O request reordering in the SSDs. In addition, it's utilizing shared memory in order to allow for much faster software upgrade process or recovery from SPDK target application crash. This means the whole shutdown and startup cycle can be executed in under half a second. Next is the L2P. As mentioned, FTL requires a mapping table that will be able to use to point to the most recently written user data. The requirements for the L2P is 1 GB for each 1 TB of disk space for drives smaller than 16 TB, and it increases to 2 GB per 1 TB for bigger drives.
The default behavior is then to store the hottest 2 GB of LTP in the DRAM cache and page it in and out asynchronously in order to access the physical location on the drive. All user writes are committed first to the persistent cache working in write-back mode. This introduces many of the benefits that CSAL gains from. After the big data workloads, we generate temporary data with some locality. This means that by keeping it in the cache until they are invalidated, saves the less enduring QLC media from being written to. At the same time, since the same data is often read from quite often, it will gain a performance boost from accessing the faster drive. Additionally, since the data is actually committed to the cache drive media during user write operation, it is safe from any power failure scenarios. Next up is the storage analytics part. At the moment, its main functionality is to be able to classify and balance the write performance of user I/O and any internal requests, in order to stabilize the bandwidth. In the future, we expect to classify the user I/O to allow for better tenant isolation, as well as give some QoS guarantees. When it comes to the NAND storage, the question is how to deal with the high capacity media. With the right shaping characteristics of CSAL, the SSD sees a lot of high block size sequential workloads, which makes it very easy for the firmware to keep its media healthy. The right amplification factor from the SSD point of view is extremely close to 1 in our tests, which means even less internal over-provisioning is needed, leading to cheaper or bigger drives. In the future, we're expecting to add zone namespace drive support, for which I'll present some preliminary results later. These ZNS drives will make it much easier to achieve tenant isolation, and we expect them to be able to drive costs even further down, since the amount of over-provisioning should be lower still, and the DRAM requirements will be reduced as well. If trends continue, PLC media will have even higher NAND engine consideration in order to fully utilize them. The final block to be added is RAID. The idea here is that with the size of SSDs increasing, it makes more and more sense to do any rebuilding locally instead of having it distributed via network. Additionally, one of the big problems of traditional RAID 5 and 6 is the performance hit of any writes smaller than the stripe size, as well as the issue of write holes. I'll get into detail about RAID later, but in short, the current architecture of CSAL makes it a very attractive way of addressing both of these problems within the current logic. So to sum it all up, is the CSAL architecture enables high capacity NAND in cloud while preserving the traditional random block access. It achieves this by intercepting random workloads in the cache device and then translating them to the larger writes into the NAND. Now let's look at the performance results. We'll take a look at CSAL and compare it against alternatives with some fire workloads first. Here we can see the results from a set of 10 workloads created by Alibaba, which were designed to either simulate the cloud environment in a simple file script or to really stress test the architecture. As a comparison, we can see the baseline HDD results, where each job had its own drive to run against. The next column is the raw single QLC drive split into 8 partitions. While some workloads benefit from the switch to NAND, clearly see the issue of the big indirection unit, as any 4 KB block size job suffers a lot from it. Next up is the Open Cache framework, which is also available in SPDK. Set up similarly to CSAL, with Optane cache device backing a QLC-based device, while it improves the results in most cases, for some workloads, like the random 4K writes, there just isn't much that can be done. And finally, CSAL performance results, for which I'd like to point out a few workloads in particular. First up is the workload number 4, where we can see the benefits of using a cache device in general, both for CSAL and OCF. Sub-ZIP-FIAN setup means that most of the actual work set fits in the 800 GB cache, so little of it trickles down to the slower QLC drive. Next is the random 4K workload. While both HDD and lone QLC struggle with it, CSAL's strategy of gathering the data for big sequential writes makes it extremely more performant. Last workload of note is the sequential 4K workload, where again we see QLC issues with a misalignment against the indirection unit. CSAL still leaps ahead with the aggregation of user data into larger blocks. Next up, we'll take a look at the results from Ali's big data performance results. Here we can see the comparison of the setups. The old D2 instance using Cascade Lake CPUs paired with HDDs, going against the D3, which is working with Ice Lake and CSAL. The D series of instances are meant to be cost-effective and high capacity, designed for big data analysis, like HDFS, Spark, and Hadoop. Both of these instances have equivalent storage capacity, but the newer D3 has a lot less CPU cores. With the increased core size amount, Alibaba is now capable of running 2 such instances on a single server, with some cores set aside for SPDK and CSAL logic. First, let's take a look at the results from TPC-DS, a decision support benchmark, a very CPU-intensive workload. You can see that even though we nearly have the amount of CPU cores in the system, the overall performance stayed near the same level. But the real deal are the results from TPC-XHS, which is a storage-intensive big data system benchmark. Visible clearly are the gains from CSAL, with workloads gaining from 70% up to nearly tripling in performance, eliminating the storage bottleneck in the instance. In most cases, Alibaba's customers will gain double the performance in these storage workloads for the same price. So now that we know how CSAL performs, let's see how to actually work with it. First, let's talk about the requirements. There are a couple, and most of them are concerning the drives themselves. So what CSAL actually needs from its cache device? It needs a DIX-capable device with 64-byte metadata, 4 kilobyte sector, and the size needs to be at least 5 gigabytes. So what DIX means is that the metadata is sent as part of a separate buffer. It's not interleaved with the data buffer itself. So when we look at the output of NVMe CLI, here we can see this MC field near the end. And this field tells us which mode of metadata the drive itself supports. When the bit number 1 is set, counting from 0, this means that the drive supports DIX metadata. Then we need to format it in the correct LBA format. Over here we can see that we have picked the 64 metadata size and the 4 kilobyte block size. And last, when we actually look at the output from get BDEVs in SPDK, you can see that the MD size is indeed 64 bytes and it's not interleaved, meaning that the drive was formatted correctly. Next, we need to look at the backend device or base device. Here we only require that the drive itself has 4 kilobyte sectors and the size of the drive itself is at least 20 gigabytes. And last, we potentially need an expanded huge page amount, because we can set how much LTP is used in the DRAM. That takes part of the huge page budget. And by default, SPDK uses 2 gigabytes, same as the amount of LTP. So if you want to create multiple FTLs or even more than one BDEV, because FTL needs some other BDEVs, then we'll probably need to increase this amount. Over here, you can see that the huge amount has been increased to 8 gigabytes. Now that we've got our drives ready, let's get started with setting up our SPDK itself and the BDEVs. First of all, we need to start the SPDK target application, either SPDK targets itself, vhost, iSCSI target, or any other target that we wish to use. Second of all, we need to attach the NVMe devices. Since we need both a base and cache device, here we can see the attached controller for both of them. And finally, just need to create the FTL itself. The only required parameters are the name, both of the FTL, and the base and cache devices. Here, the -C NVMe 0 and 1, that's the cache device. And as part of its output, it returns the name of the BDEV as well as the UID. The UID is used when trying to load the FTL instance. There are a couple of recommendation and notes around create FTL. First of all, we recommend the cache device to be around 5% of the base device capacity, though we have tested it with as low as 2.5% with good performance. Second of all, the first creation of FTL instance will take longer than usual due to the need for scrubbing of cache device. This is why you can see the timeout has been increased to 600 seconds, though for an 800 gigabyte drives it takes around 2 minutes to scrub. Any loading after that will not take any longer. And finally, we recommend a read bandwidth limitation on top of the FTL BDEFs. This is a requirement that we plan to drop in the future once we have better scheduling. Though at the moment we recommend around 2 to 3 gigabytes of read bandwidth on top of FTL itself. Now let's take a look at the optional parameters for FTL Create BDEF RPC. First, over-provisioning. This argument tells FTL what percentage of the base device should be set aside for garbage collection activities. The higher the value, the better the performance of random workloads, though at a cost of a smaller resulting device. The default value is 20%, though 10% performs well in the vast majority of cases. Next, LTP DRAM limit. Since logical to physical table has a fairly large DRAM footprint, for a 16 TB drive it takes roughly 16 GB, FTL by default will store only a portion of it in the DRAM, paging it in and out as necessary. This parameter allows the user to set the specific upper bound. We have found that the default value of 2 GB provides a good cost and performance characteristics for a 16 TB device. The core mask allows the user to set the CPU cores on which FTL logic should be run against. By default, SPDK will schedule the pollers. However, setting the value allows the user to more explicitly group together, for example, vHost controller and FTL. The fast shutdown argument tells FTL if it should utilize the shared memory during shutdown of SPDK target application. If used, the shutdown startup process will be roughly an order of magnitude faster, compared to performing a full clean shutdown, which would synchronize all metadata to the drives. And finally, UUID. As seen before, creation of FTL generates a UUID for the BDEF, and when loading the BDEF instance in the future, this parameter should be used in order to restore the blocked device. Now we can look at the BDEF FTL delete. Utilizing this RPC call will cause FTL to synchronize its metadata to the base and cache devices and shut itself down, ready to be loaded in the future. Other than the name of the FTL BDEF, this RPC only has one other optional parameter, fast shutdown. Similar to the creation case, this allows to specify if FTL should utilize shared memory to speed up the shutdown process by keeping some metadata in the shared memory and skipping synchronization of it to the device. Here we can see this comparison of regular and fast shutdown. The slow path takes roughly 800 milliseconds to shut down, around a quarter of a second to shut down itself, and then the startup takes another 600 milliseconds, while the fast path will be done fully in under 100 milliseconds. Next call we'll be describing is the BDEF FTL unmap. This allows for a management path for clearing or trimming data from an FTL BDEF. It can be useful in preparing the instance to be used for the next user. It has one limitation compared to the usual trim operation. It can only process unmaps aligned to 4 megabytes, both for the starting LBA and its length. Other than that, it behaves similar to trim. Any unmapped region will return zeroed out data on reads from it, and it will improve garbage collection process by marking to FTL unused regions. The last RPC we'll be looking at is the BDEF FTL Get Stats. It returns detailed I/O statistics from a specific FTL instance divided into several groups. The usual section returns the information and I/O requests from the immediate upper layer, any BDEF created on top of FTL, or the user itself. We can see the division between read and write requests, the number of I/Os of the given type, and the total number of blocks read or written, and any errors detected by FTL. The CMP describes the statistics of compaction, the process of moving valid data from the cache to the base device. GC is garbage collection, that is, moving and reclaiming free space in the base device itself. MD base describes all internal FTL metadata written and read from the base device, while MD and the cache describes the same information for the cache device. Finally, the LTP section will show the statistics for the paging in and out processing of the logical to physical mapping table. I would like to recommend two sources for up-to-date and detailed documentation. JSON RPC, which will have the up-to-date descriptions as well as examples of all the RPC calls presented today, as well as FTL ND, which will have a high-level look and explanation of the terminology used by FTL. Now, I'd like to talk a little bit about the future of CSAL, which areas of the existing code we were aiming at improving, and new functionalities and modules we're going to be expanding into. First off is RAID 5F and RAID 1. There are new BDEV modules added to the already existing RAID 0 implementation. They should have the full implementation of such core features like rebuilding of degraded array and automatic error handling. In the CSAL ecosystem, we expect RAID 5F to be used as a base device under FTL, with RAID 1 potentially being used as the cache device. Second, zoned namespace drive support. ZNS SSDs are a type of device that allow for much easier tenant isolation and potentially lower prices in the drives themselves due to lower overprovisioning. However, they only allow sequential writes and require management of the zones. But sequential writes is exactly what CSAL is already doing, and it's managing its internal FTL state in a similar way to ZNS drives, so the overall logic is already there. With improved I/O scheduling, we're aiming at removing the recommendation of having read bandwidth limitation on top of FTL BDEVs. All the read-write balancing will be done internally. We expect PLC drives to be another step in reducing the costs of SSDs, the lower endurance and random workload performance drop. Thus, we expect that, with some tweaks inside the FTL logic, to be able to improve those metrics greatly. As for the last new feature improvement, we're working on being able to more accurately determine the best placement for incoming user write data. This will improve CSAL's garbage collection logic, leading to lower write amplification factor and increasing both performance and endurance. So, with these 5 high-level topics described, I'd like to get into more depth with RAID and zoned namespaces. Both RAID 1 and RAID 5F are currently under active development in SPDK, with some initial patches of RAID 5F being already present in SPDK version 22.09. However, first, a quick explanation: what is RAID 5F? It's an implementation of RAID 5 where the write unit size, that is, the smallest amount of data that can be written, is equal to the stripe size. The F in the name then stands for full stripe writes. With such a restriction in place, it allows for much more streamlined RAID logic. It no longer needs to consider costly locks in order to synchronize 2 smaller writes, modifying the data in the same stripe, both of which would need to do a read-modify-write operation, which increases the write amplification factor. When used in conjunction with FTL, we will also be avoiding write hole, a potential silent data corruption that could occur when a power failure occurs when only part of a stripe has been written. Thus, we expect that RAID 5F will be mostly used only in combination with FTL as a base device. RAID 1, on the other hand, won't have any such restrictions. While we're expecting to use it as a cache device in the CSAL ecosystem, its compatibility means already existing use cases should have an easier time adapting it. As mentioned near the beginning of the presentation, one of the problems of QLC drives in particular is tenant isolation. Executing different workloads from multiple users means that eventually data gets mixed together into SSD, causing a performance drop for everyone. One of the potential solutions for this problem are zoned namespace drives. They allow for placing each tenant in a different zone, which is a small section of the device, around 1 GB depending on the vendor. With this, any write and validation that occurs from random workloads is limited to just that user's portion of the SSD. As mentioned earlier, there are a few restrictions though. The writes to a zone need to be sequential, so your user needs to keep track of mapping of logical to physical addresses. And also the user needs to actively manage that mapping in the zones, that is, do some garbage collection, in order to free zones for further use. This is extremely similar to what FTL was already doing, So the introduction out of the way, I'd like to show you some preliminary performance data on ZNS SSDs. As you can see, we're going to be executing 4 very different workloads: sequential, uniform random, and 2 ZTL workloads with different distributions. The 2 drives taking part in the comparison are both Western Digital, both in similar performance and endurance characteristics, but one is a zoned namespace drive, while the other a standard SSD. As you can see, the overall write amplification factor has dropped by about 40% on the zoned namespace drives compared to regular SSDs. This translates to a couple of things: that much better endurance and performance, since more user writes can be utilized by the drive rather than being spent on internal garbage collection. It also means better quality of service, as the workloads from multiple tenants won't be in as much conflict with each other. The code for ZNS supporting FTL wasn't at production level quality though yet, and isn't available in SPDK 22.09. We expect to be ready with the patches after the January SPDK release. So I'd like to thank you for your time and sticking with me through the end of the presentation. I hope you found it useful and interesting. Have a good day and enjoy the rest of the summit.